Welcome back. So, last class we were discussing the probability generating function, which is a transform which is typically used for integer valued random variables, right. So, there was the small clarification I had to make. So, the region of convergence of the PGF, I said, so it is they are disks for non-negative integer valued random variables, and if the random variable potentially takes negative values, they are generally annular regions, right. But the region of convergence always contains the unit circle, right. So, this is one clarification I want to make. Today we will study the moment generating function, which is actually defined in general for any random variables, not necessarily discrete or continuous or otherwise. And the reason we will see the reason it is called moment generating function, because it generates the moments, the nth powers of the expected nth powers of the random variable. MGF. The function mx from R to 0 infinity defined by mx of s equal to expected value of e power sx. The domain or region of convergence of mx is the set dx equal to the set of all s for which mx of s is finite. So, the moment generating function of some random variable x is like an exponential moment, okay. The expectation of e power sx, where s is the parameter, okay. And it obviously this may not exist everywhere, and the domain in which, or the region of convergence where this guy is finite, is called the domain or the region of convergence of this moment generating function, okay. Now, notice that, so there is, so I have defined it as a function that maps R to 0 infinity, right. So, what I am essentially saying is that this s is something real, some real number, right. So, again, so strictly speaking, moment generating function ought to be considered a function of a complex variable, okay. So, strictly speaking, that it is analogous to the Laplace transform, okay, so we will see that very soon, right. So, strictly speaking, we should allow s to be complex, right, but throughout we will be a little bit sloppy about this. Part of the reason is that we have not really defined the expectation for complex valued random variables, right. We have only spoken of expectation of x, where x is some real valued random variable. We have not really spoken of, so e power s, if s is complex, e power sx will be complex, and we have not really described complex random variables in any detail, right. So, ideally we should have s is complex, but I am kind of pushing it under the carpet, okay. I am not going to be very serious about this, and for this reason, even for there are many theorems and results on the moment generating function which really require a fair amount of complex analysis to prove and understand properly, right. So, many of, in that sense I will only be quoting results and using some properties from complex analysis without being very serious about deriving them or proving them. Okay. Okay, so this is expectation of e power s x. So if x were to be discrete, this is you would just sum up the PMFs, right. So for example, if x is discrete with PMF Px of x, then mx of s will be sum over x e power s little x Px of x, right. And if x is continuous with density f x, then m x of s is equal to integral e power s x f x of x d lambda dx, you can call it whatever you want. Okay. You are integrating x basically, maybe. So just to be clear, let me just write dx. Okay. All right. So it is in this sense that, so for continuous random variables, this moment generating function is exactly analogous to Laplace transform, except for that little minus sign you use for Laplace transform, right. Usually you put a minus here for Laplace transform, but otherwise it is the same thing. Okay. And just like in Laplace transform, you consider s as a complex number, right. Ideally that is what you should do here also, okay, to be precise, but we will just we will not do that. Okay. So just to keep things simple and to avoid contour integration and so on. So any questions on this? So let me give you some examples. We have an exponential random variable with f x of x is equal to mu e power minus mu x for x bigger than or equal to 0. Then you have m x of s is equal to integral mu e power minus mu x e power s x dx, right. This is from 0 to infinity. This is equal to, so this, if you just do this integral, you will get mu over mu minus s or s mu minus s, okay, and this is valid for s less than mu. Okay. So yeah, so if you can just, for now s we are treating s as a real number, right. So we just do this integral, and you can see that if s is less than mu, e power minus mu x. So if you just take this up, you will get this, just simplify this. But if s were to be bigger than mu, this e power s x is growing faster than e power minus mu x, right. So you will get infinity, right. In that case, the moment generating function is plus infinity. Okay. So again, so there is one remark I want to make here. If you had, so again, right. So if you were doing this as a Laplace transform, right. So this will become a integral of a complex function, right. So technically, in order to be rigorous, you have to do this as a contour integral, Okay. Some of you might have studied complex analysis. So, you would have to do this as a contour integral. The thing is you will get the same answer, okay, and the answer will be valid for real part of S less than mu. Okay. So, I am ignoring that bit here, okay. I am just treating S as a real number and blindly integrating it. Okay. This is clear? Second example, let us do a Gaussian. So, let us do a standard Gaussian 1 by square root of 2 pi e power minus x squared over 2 for x in R. Okay. So, I have to write out now m x of s is equal to integral minus infinity 1 by square root of 2 pi e power minus x squared over 2 e power s x dx, right. Fine. How do you do this integral? There is a very standard trick to do this integral. You have to square, I mean you have to complete squares in the top, right. You remember that, it is an old trick. So, you have to multiply, you have to I think do that s squared over 2 and then you do, so then multiply by e square e power minus s square over 2 and then you will have a perfect square in the top, right. You will have e power minus x minus s squared over 2, right, correct, with me. So, this is just algebra, right, this is a standard trick and then this integral is a standard Gaussian integral, right. So, this integral will become 1, okay. So, the answer will be e power s squared over 2, okay, and this is valid for all s, okay. I will say that for all s in R, okay. Actually this is, in fact this is the moment generating function for all complex values of s also, it is valid in the whole complex plane. This is not valid in the whole complex plane, it is valid for real part of s less than mu if s were to be complex, okay. So, I am so far I am just doing all this as real integrals, okay, which is not technically speaking the full means fully correct, okay. Actually when we do Fourier transform, this issue will bite us even more, okay, when we do characteristic functions, right, which is like a Fourier transform, this will bite us even more, but for now it is okay, okay. So, that is exponential, this is Gaussian, and finally let me do Cauchy. So, if you have f x of x is equal to 1 over pi 1 over 1 plus x squared x in R. Now, you try to do this integral m x of s equal to integral minus infinity to infinity e power s x over pi times 1 plus x squared dx, right. Now, what happens in this case? If s is equal to 0, you get, if s is equal to 0, you get 1, right. You are just integrating the PDF itself, right. So, by the way, I mean if s is equal to 0, anyway you get the expectation of this whole thing will become 1, right. So, it is always 1, that is one of the properties I am going to state, right. So, this will become 1 for s is equal to 0. But if s is, again pretending s is real, if s is greater than 0, you have a growing exponential competing with a decaying 1 by x square type of a term, right. So, that will be infinity, right. But if S is negative, what happens? You have the opposite problem, because on the negative side it is growing, right, and 1 by x square is the decay on the negative side as well. So, what you can conclude, if S is not is equal to 0, this is not 0, this is always infinity, right, infinity otherwise, right, with me. So, if you are restricting S to real values, only for S is equal to 0 is it defined, otherwise it is infinity, it is not. So, the region of convergence in this case will be just S is equal to 0 on the real line, it is only for S is equal to 0 is the MGF finite, okay. But S is equal to 0 is always a part of the region of convergence, because as you can see the moment generating mx of 0 is always equal to 1, right, by definition. So, for this particular, so okay, there are 3 different cases, right. So, here there is a certain range where it is finite, certain range where it is not in the region of convergence. Here for all values of S, the mx of x exists. So, the region of convergence is the entire real line in this case, and here there is only one point in the region of convergence, only the origin, right. But origin is always in the region of convergence, and that is all there is in this case. There is no further there is no further points in the region of convergence. Is that clear? So, that brings us to the question, is it enough to specify the moment generating function in order to specify, if I just tell you this is the moment generating function and this is the region of convergence, is it enough to specify the random variables distribution, or the random variables density in this case completely, right. So, if I were to give you, this is my moment generating function with this region of convergence, is it necessarily true that, so for the exponential this is the moment generating function, but is this true that if I only give you this, can you conclude that the, can I uniquely say that it is this PDF, or for that matter for the Gaussian, if I give you this is my moment generating function e power s square over 2 for all s, can you tell me that the random variable is the standard Gaussian, right. So, more generally if I give you the moment generating function and region of convergence, can I tell you, can you tell me the distribution uniquely, right. So, that is the, what do you think? Yes, yes or no? No, who says no? Yes. So, suppose I give you this, suppose I tell you that the it is equal to 1 for S is equal to 0 and everywhere else it is undefined or infinity, right, infinity actually. So, then what do you say, does it have to be Cauchy? So, in fact, I can have 1 over 1 plus x cube, right, you will get the same answer, correct. So, if this were to be not 1 over 1 plus x square, but 1 over 1 plus x cube with some other constant in front, by the same argument you can conclude that, or 1 over x to the 4 for that matter, right. So, you can easily conclude that it will be the same, moment generating function will be defined only for s is equal to 0 and undefined or plus infinity for s not equal to 0, correct, right. So, what do you think? So, generally the answer is no. So, I just proved that the general answer is no. If I give you the moment generating function just like this for example, there is no way you can figure out the distribution. But it seems like, I mean, if you tell me something like that or something like this, it seems like you can uniquely identify what the distribution is, right. So, the complete answer to this turns out to be very interesting, but in order to appreciate it you have to know some well, it requires some tools from theory of analytic functions. So, the answer is the following, if you specify if you give me the moment generating function not at one point, but in some tiny neighborhood of the origin of S is equal to 0. If you specify in any tiny neighborhood around the origin, then that is enough to specify the density uniquely. The distribution is uniquely specified by specifying the moment generating function in any tiny interval, right. The interval can be very small or very big, does not matter. So, you do not even have to tell me, for example, that e power s square over 2 is the moment generating function in all of real line. If you just tell me this is the form for a tiny interval around the origin, then it has to be Gaussian in this case, in that case it has to be exponential and so on. But if you just give it to me at one point, it is clearly not enough, right. So, I will just state this as a theorem without proof. Okay. This again goes back to the theory of analytic functions. Analytic functions are these, you can think of them as these very nice functions which get completely specified if you specify them in a small interval. Okay. Mx of s is finite for all s minus epsilon epsilon. So, this epsilon is greater than 0. Okay. Epsilon is any positive number, it can be very small also, okay, as small as you like, it can't be 0, it has to be strictly positive. Suppose you tell me that m x of x is finite in that little interval around the origin, then m x of s uniquely determines the CDF of x. If x and y are two random variables such that m x of s equals m y of s for all s in some tiny interval minus epsilon to epsilon, again epsilon is positive. Then x and y have the same CDF. So, this is like a uniqueness of moment generating function. Okay. So, it is not enough to specify it at a point or a few points, but if you specify the moment generating function in a tiny interval, right, no matter how tiny it is, if you specify it in an interval, the CDF is uniquely specified. Furthermore, if you have two random variables, let us say you know nothing else about them, but you do know that they have the same moment generating function, not necessarily everywhere. Okay, they have the same moment generating function in some very tiny interval around the origin. Okay, see all moment generating functions agree at the origin, right, because m x of 0 is equal to 1. But I am saying that m x of s and m y of s do not just agree at the origin, which they have to, they agree in a tiny interval around the origin. Okay. Then it is necessarily the case that the moment generating functions have to agree in their entire regions of convergence, and the random variables have the same CDFs. Okay. So, this kind of a result is possible because these so called analytic functions, this moment generating functions, whenever they exist, in a neighborhood, they are analytic functions of S of the complex variable S actually, and these analytic functions have some very where they have some very tight properties. Okay. So, you cannot have two analytic functions agreeing on an interval and then differing elsewhere, okay, because you cannot make analytic functions by stitching together, right, because they have some very tight structure. Okay. You cannot stitch together functions and make them analytic, it never works that way. Okay. So, that is why this theorem holds. Okay. This proof is beyond the scope, as I said, because it requires machinery from complex analysis. Which one?
Around 0.
There is no further conditions, right. I mean, I have not said anything else here, right. If they agree in an interval, they agree everywhere. Actually, that has nothing specific to do with moment generating functions. It is true for all analytic functions. It just so happens that the moment generating functions, whenever they exist in an interval, they are analytic. Okay.
Why we are specifying around the origin? It can be anywhere.
See, the thing is, so if you take that, let us say S is equal to 0, mx is always, all moment generating functions have the value 1. Okay. So, what I require is that the function be function agree on some interval. Okay, that interval can be anything, right. If it agrees on minus epsilon 1 to epsilon 2, it necessarily agrees on some minus epsilon to epsilon, right. So, I can take there is no loss of generality in taking a interval like that. Okay. Generally, if an analytic function agrees on any interval whatsoever, it will, that is enough.
Taking 0 because infinity is always.
It is always defined, right. 0 it is always defined, but it is not clear that it will be defined in an interval around 0 as in this case, right. But if it is defined, it is uniquely specified, no matter how tiny this epsilon is. Yeah, you can have minus epsilon 1 epsilon 2 if you like, there is nothing very sacred about keeping the same epsilons, right. So, is that clear? So to go back to this, if you give me a function like that and specify an interval in which it holds, then I am unique, I am sure that this is an exponential and that is a Gaussian without even specifying it for, let us say, the whole of real line. If you tell me that the MGF is e power s square over 2 in a tiny interval around the origin, then it has to be a Gaussian, the random variable, right. But here you cannot specify it for an interval, right, it is too bad, it is only defined for one point. In that case, it is not unique. Okay. So, okay, so that means, so at some level I must be able to, if you are giving this kind of some functional form to me in an interval, I must be able to invert the moment generating function and get back my CDF or PDF or as the case may be, right. There are actually explicit formulae in terms of the moment generating function to get back your, so to get back your in this case density, let us say, right. These formulae are basically similar to the inverse Laplace transforms, okay. But again we will not go into it because it requires. So, what is an inverse Laplace transform like? It is a contour integral, right. It is an integral of a complex function over a certain contour, right. So, because that is a little bit beyond our scope, we will not actually perform contour integration to invert any transforms. After all, if I tell you that the MGF is 1 over 1 minus s, you can just do some pattern matching and figure out what the random variable is, right. So, what the approach we will take is somewhat more what I might call practical rather than very mathematical, just that if you just pattern match, if you see a transform like that, you know it is Gaussian, right. So, we will just figure out some transforms for some popular random variables, put that in your, keep that in your mind or put that in your formula sheet for your exams, and you just do pattern matching, okay. We will not worry about contour integrals. Yeah, so most of you must be experts on Laplace transforms, right? Some of you will just know, will probably have like memorized a bunch of tables of transforms and such. So, in that case you can pattern match. If you have not that type, you put it in your formula sheet, no problem, right. So, properties. Properties of MGF. Mx of 0 is equal to 1, right, that is the most trivial property, that is by definition. Second property, moment generating property. Which is why the function is called the moment generating function in the first place, right. So, this I will put as a theorem. Suppose mx of s is finite for s in minus epsilon 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 is positive. Then the derivative with respect to s evaluated at s is equal to 0 is equal to expectation of x, and generally the mth derivative ds m at s is equal to 0 is equal to expectation of x power m. Okay. So, what this is saying is that if you take the derivative of the moment generating function with respect to s and set s is equal to 0, you get the expectation, which is the first moment, and generally the nth moment, the mth moment is obtained by evaluating the mth order derivative and taking s is equal to 0. Okay. So, this is again, so if you want to prove this theorem, so there is a, I mean there is, I will just at a very hand wavy level, this is what is happening, right. You are taking d ds of expectation of e power s x, right. So, if you tolerate me taking the derivative inside, okay. So, if you do expectation of d ds e power s x, then this will be expectation of s times e power s x, correct. I am differentiating with respect to s, right. So, x times e power s x, correct. So, this is equal, so and then I set s is equal to 0, then I get expectation of x, right. So, yeah, I mean I guess if you are an undergraduate student, this is the proof for you. If you are a graduate student, you will have to question this step, right. I am essentially taking the derivative inside what is this expectation, after all it is integral, right, it is an integral x d e power s x dp, right. So, this requires a somewhat serious proof, okay, not a difficult proof, but this will be in your homework. Okay, it is I will put this in your next tutorial. This requires a proof, I believe it's you have to invoke dominated convergence theorem somewhere in order to yeah, it requires an invocation of the dominated convergence theorem, that is your hint. Okay. And similarly for the mth derivative, again if you are willing to buy the step, you can differentiate this m times and you will get x to the mth here, right. So, you will get the mth moment. Okay. So, the only real mathematical thing is in taking in the you are essentially differentiating inside the integral, that requires a justification. Okay. It is not always true, okay, it requires justification. After all, the derivative is, so let me give you one more conceptual hint. So, the derivative is some kind of a limit, correct, limit h tending to 0 of something, right. So, you have expectation is an integral and what is outside is a derivative which is like a limit. So, you have limit of integral, and if you have to integrate interchange it, you have to have integral of limit, right. So, you must invoke either MCT or DCT, you know only two ways to do it. In this case it turns out that DCT will do the job. Okay. So, I will not say anything more about the proof, because you will supply this step and then you are fine. Okay. So, that is property number 2. Okay. Property number 3, if y equal to a x plus b, a and b are real numbers, then m y of s is equal to e power b s m x of a s. Okay. This is actually a fairly simple change of variable. Okay. Fine. So, in particular, so as an example, if you have x is your standard Gaussian and if you have y is equal to, well, sigma x plus mu, y is equal to sigma x plus mu. In this case, then y will be, you can easily show that y will have mean mu and standard deviation sigma, be a variance sigma squared, right. So, then y will be n mu sigma squared, and in that case m y will be e power mu s times e power sigma squared s squared over 2. Okay. So, you know the mx of s for the standard Gaussian is e power s squared over 2, right. I am just using this result to compute the moment generating function for non standard Gaussians as well, n mu sigma squared, right. I can compute the moment generating function.
So,
yes.
the second property, expectation of units to Sx. So, the expectation of units to Sx converges, then can we interchange the definition proof?
That is what you have to prove, right. I am saying that this is valid, this interchange is valid, but it is not always valid, it is valid in this case. You cannot arbitrarily interchange derivatives and integrals. Okay.
If the over integral converges, then we can
No, you need to invoke dominated convergence theorem. This requires this is not this requires maybe 4 steps. It is not one step. Okay, it's you will do it in your homework. It's a guided proof that you will do. Okay. Good. Now, finally, property number 4. If you have z equal to x plus y, x and y are independent, then you can show that m z of s is equal to m x of s times m y of s, and this is because expectation of e power s z. So, e power s z is equal to expectation of e power s times x plus y, that is equal to expectation of e power s x times e power s y. Now, you know that x and y are independent, therefore, any functions of x and y are independent, and since then therefore, these two are independent, e power s x and e power s y are independent, and independent random variables are uncorrelated, right. So, this will become e power s x times expectation of e power s y. So, here is where you need you are using independence here. Okay. And similarly, if you have n random independent random variables, you will just multiply all the moment generating functions in order to get the moment generating function of the sum. So, this is valid for discrete, continuous, any kind of random variable, right. We have not assumed anything in particular. So, this is exactly like in signals and systems. If you are instead of convolving functions, you multiply Laplace transform and invert back, right. That is exactly what you are doing here. So, if x and y had, let us say they had densities, then you would convolve the densities, but that convolution is an awkward operation. So, it is better to take transforms, multiply and transform back, right. So, if you want to example, if x 1 is exponential of mu 1 and x 2 is exponential mu 2 and x 1 and x 2 are independent, and then if z is equal to x 1 plus x 2, then you have m z of s will be the product of the two moment generating functions, right, which will be mu 1 mu 2 over mu 2 minus s times mu 1 minus s, right. I am just multiplying the two moment generating functions, and this will be valid for s less than the smaller of the two, isn't it, minimum of mu 1 comma mu 2. Okay. So, this is the moment generating function of the sum, correct. Now, how will you find the if you want to find what the distribution of z is, you will have to invert this moment generating function, right. So, now you can use some of your Laplace transform tricks, what you are used to in Laplace transforms, right. Normally, if you have something like this, you write a partial, what is it called, partial, yeah, right. So, you will write it as a over mu 2 minus s plus b over mu 1 minus s, find a and b, and then you know what to do, right. So, that is fairly standard. I think you can proceed from here. If mu 1 were equal to mu 2, you will get mu minus s whole squared, okay, and that will be the transform of your second order Erlang, because you are adding two exponentials. Okay. Okay, so good. Then finally, let me just state the final property before finishing. If you had a sum of a random number of random variables, let us say z is equal to sum over I equals 1 through capital N x I, where x i's are I I d with m g f m x, and n is independent of xi's with PGF Gn and MGF Mn. Then so this is a situation we have considered before. I am just trying to write its moment generating function. Mx of s is given by Gn of Mx of s, okay, or equivalently which is equal to Mn of log Mx of s, okay. So, Gn is your PGF from the previous class, okay. The proof of this is using the law of iterated expectations, is very similar to the proof we derived in the previous class, okay. This is fine. So, the most this formula is most useful in an example of this following kind, where you have xi's are IID exponential with parameter mu, let us say, and n is geometric with parameter p. I think we considered this example earlier, did not we, where you had a geometric sum of exponentials, right, and I think what we did there is just brute forced it, wrote out the whole thing and figured out that there is some answer, right. Here you will get a very explicit answer, because here you have Mx of s is what, mu over mu minus s, right, where s is less than mu, and you have Gn I know, right. So, Gn of s, Gn of, if you like, Gn of z is what I used, right. What is the PGF of this? From previous class I had Pz over something like that, isn't it, 1 minus Pz, is that right, correct, and this is valid whenever the argument is less than 1 over 1 minus p. So, if I were to blindly substitute here, so my mz, z is of course my geometric sum of exponentials, mz of s will be equal to p. So, I have to compose, so I have to take Gn of Mx of s. So, whenever I have Gn of z, in place of z I have to write this whole thing, right. So, I have to write p mu over mu minus s over 1 minus p mu over mu minus s, right. So, I have to take care of the regions of convergence, of course, right, just do that, and I think you just simplify this, you should get mu p over mu p minus s. Actually, I did not even compute that because I know the answer. The answer has to be an exponential with parameter mu p, right. You remember the taxi example, or what it is, a taxi or alpha particles, either way, either example will do, right. You are waiting for taxis which arrive like with exponential durations, and with probability p they are occupied, maybe probability 1 minus p they are occupied. So, you have to wait for a geometric number of taxis, each of which takes an exponential amount of time to come. So, the total time you wait is exponential with parameter mu p, okay. So, this is very easy, right, this is like 3 steps rather than doing that big summation in the previous case, okay. I will stop here.